Welcome to this coding tutorial. Today, we will be tackling problem number 31, titled Next Permutation. This problem is a classic interview question that focuses on generating the next lexicographical permutation of a given array. Stay tuned as we dive into the problem, explore various approaches, and analyze their complexities. Let's get started. The next permutation problem is a well-known algorithmic challenge where the goal is to rearrange the elements of an integer array into the next lexicographical order. This means we want to find the smallest arrangement of the numbers that is greater than the current one, based on dictionary-like order. For example, if the current order is 1, 2, 3, the next permutation would be 1, 3, 2. However, if the array represents the largest possible permutation, like 3, 2, 1, then we need to wrap around and transform it into the smallest possible permutation, which would be 1, 2, 3. Importantly, this rearrangement must be done in place, meaning we cannot use extra memory or create new arrays. The function modifies the input array directly and does not return a separate result. The input to the problem is an integer array called nums, which represents a valid permutation of numbers. This array can include duplicate numbers, so it is not always guaranteed to be made up of unique elements. For the output, you will modify the array nums in place to reflect the next permutation in lexicographical order. Since the changes are made directly to the input array, the function doesn't return any value. Let's take a look at some examples to better understand the task. For instance, if the input array is 1, 2, 3, the next permutation would be 1, 3, 2. This is because 1, 3, 2 is the smallest arrangement of the numbers that is greater than the current one. In the example where the input array is 3, 2, 1, the result would be 1, 2, 3. Here, the current permutation, 3, 2, 1, is the largest possible arrangement of these numbers. Since no greater permutation exists, the array is rearranged into the smallest possible permutation, which is sorted in ascending order. Another example is with the array 1, 1, 5. The next permutation in this case is 1, 5, 1. This involves rearranging the numbers to find the smallest lexicographical order that is greater than 1, 1, 5. The problem comes with some constraints and important edge cases to consider. First, the array can have a length between 1 and 100, and its elements range from 0 to 100. If the array contains only one element, there is no next permutation, so the array remains unchanged. For example, 1 stays as 1. Similarly, if all elements in the array are identical, like 2, 2, 2, the array remains the same since no greater permutation exists. Lastly, if the array is already in descending order, like 4, 3, 2, 1, it represents the largest permutation. In this case, you would rearrange it into ascending order, resulting in 1, 2, 3, 4. These edge cases highlight the importance of understanding both the smallest and largest permutations in the context of this problem. Let's start by considering two approaches to solving the problem. The brute force method is the most intuitive. It involves generating all possible permutations of the given array, sorting them, and then identifying the permutation that comes immediately after the current one in lexicographical order. While this approach is straightforward to understand, it is computationally infeasible for large inputs due to its factorial time complexity, O(n), as the number of permutations grows exponentially with the size of the array. Additionally, sorting these permutations would add even more overhead, making it impractical for real-world use. To address this, we can adopt a more efficient strategy by identifying key properties of permutations. First, we observe that the next permutation is determined by the first decreasing element when traversing the array from right to left. This is called the pivot. To achieve the next lexicographical order, this pivot must be swapped with the smallest element to its right that is larger than it. Finally, to complete the arrangement, the suffix of the array after the pivot is reversed to ensure it is in the smallest possible order. These observations form the foundation of our optimized approach. Using this optimized approach, we avoid generating all permutations and directly compute the next permutation with a time complexity of O(n), where n is the length of the array. Let's break the process into clear steps. First, we traverse the array from right to left, searching for the first index I where the element at nums, I, is smaller than the element at nums, I plus 1. This identifies the pivot. If no such index exists, it means the array is sorted in descending order, and we simply reverse the entire array to return the smallest permutation. However, if a pivot is found, we proceed by locating the smallest element to the right of I that is larger than nums I, let's call this j. Once we find j, we swap nums I and nums j. Lastly, the portion of the array to the right of I is reversed to ensure the result is the next lexicographical permutation. This algorithm is efficient because it involves up to 3 linear scans of the array, finding the pivot, locating the smallest larger element, and reversing the suffix. The Python implementation of this step-by-step process is provided here, which begins by identifying the pivot with a right-to-left traversal, decrementing I until the condition nums I plus 1 is met. Once the pivot is identified, the next step is to find the smallest element larger than the pivot to the right of it. This is done with another traversal from the right, decrementing j until the condition nums I is satisfied. After locating this element, we swap nums I and nums j to ensure the next permutation is larger than the current one. Finally, we reverse the portion of the array to the right of I to guarantee it is in the smallest possible order. This completes the construction of the next permutation in place. Now, when comparing this optimized approach to the brute force method, the differences are clear. While the brute force approach is conceptually simple, its factorial time complexity makes it unusable for large inputs. The optimized method, on the other hand, achieves the same result in linear time and operates directly on the input array without requiring additional space. While alternatives such as library-based solutions may simplify implementation, they often involve unnecessary overhead and limit control over the algorithm's steps. This optimized approach is not only efficient but also robust, handling edge cases like descending arrays or arrays with repeated elements effectively. It strikes a balance between clarity, performance, and practical application, making it the preferred solution for this problem. To solve the problem of finding the next lexicographical permutation of an array, we aim to determine the next permutation that is just slightly greater than the current sequence. If the array is already sorted in descending order, meaning no greater permutation exists, we simply return the array sorted in ascending order, which is the smallest permutation. This concept is widely applicable in combinatorics, particularly for efficiently generating permutations. The algorithm starts with identifying the pivot. Here, we traverse the array from right to left to locate the first element where a number is smaller than the one following it. This element serves as the pivot, marking the point where the sequence stops increasing. For example, in the array 1, 2, 3, 6, 5, 4, the pivot is the value 3 at index 2, as it is smaller than the next number, 6. If no such pivot exists, it means the array is in descending order, and we reverse the entire array to get the smallest permutation. After identifying the pivot, the next step is to find the rightmost successor to the pivot. This involves traversing the array from right to left again, searching for the smallest number that is greater than the pivot. Swapping the pivot with this successor ensures that we increment the sequence in the smallest possible way. For instance, in the array 1, 2, 3, 6, 5, 4, the smallest number greater than the pivot, 3, is 4, which is located at index 5. Once we identify it, we swap the pivot, 3, with its successor, 4. The array now becomes 1, 2, 4, 6, 5, 3. This swap guarantees that the sequence is increment while keeping the change minimal. Once the pivot and successor have been swapped, the next step is to reverse the suffix of the array, the part to the right of the pivot index. Reversing this portion ensures that the elements after the pivot are arranged in their smallest lexicographical order. This is necessary because the suffix was initially in descending order after the swap. For example, in the array 1, 2, 4, 6, 5, 3, the suffix 6, 5, 3 is reversed to become 3, 5, 6. The resulting array 1, 2, 4, 3, 5, 6 is the next permutation. Additionally, when no pivot is found, meaning the array is in descending order, we simply reverse the entire array. For instance, 4, 3, 2, 1 becomes 1, 2, 3, 4, which is the smallest permutation. The key insight behind this algorithm lies in leveraging the properties of lexicographical order. By swapping the pivot with the smallest larger successor and reversing the suffix, we ensure the next permutation is generated efficiently. Each step of the algorithm, from finding the pivot to reversing the suffix, involves a linear traversal of the array, making it run in O(n) time. The algorithm is also space efficient, as it modifies the array in place without using extra memory, resulting in an O(1) space complexity. Using 2 pointers to identify the pivot and successor ensures the process is both efficient and straightforward. Edge cases, such as arrays in descending order, are seamlessly handled by reversing the entire array. This combination of efficiency and simplicity makes the algorithm both elegant and practical for solving the problem of generating the next lexicographical permutation. This code solves the next permutation problem by implementing an efficient algorithm. The goal is to transform the given array into its next lexicographical permutation. If the array is in descending order, it resets to the smallest permutation, ascending order. Step-by-step explanation *. Step 1 *. Start from the right of the array and find the first pair of indices I and I plus 1 such that nums I plus 1. This identifies the first position where the sequence is not in descending order. If no such I exists, the array is already at its largest permutation. Step 2 *. If a valid I is found, search for the smallest number larger than nums I from the right-hand side of the array. This ensures we find the next largest permutation. Step 3 * Swap nums I with the number found in step 2. This modifies the current sequence to move closer to the next lexicographical order. Step 4 * Reverse the subarray to the right of index I. This ensures the suffix is in ascending order, which is the minimal order required for the next permutation. The algorithm runs in O(n) time, as it involves a single traversal to find I, a traversal to find J, and a reversal of the subarray. The space complexity is O(1), as no additional data structures are used. This makes the solution efficient for the problem constraints. Here, we start by defining the method nextPermutation, which takes an array of integers, nums, as input. The goal of this method is to rearrange the numbers into the next lexicographical permutation. First, we determine the length of the array and initialize an index I as in 2. This index represents the first number from the right that is smaller than the number immediately following it. We use a while loop to decrement I until we find such an index or until I becomes less than 0, which means the array is in descending order and no higher permutation exists. If we find a valid I, the next step is to locate the smallest number to the right of I that is greater than nums I. This is achieved by initializing another index j at the end of the array and moving it leftward until nums j is greater than nums I. Once found, we swap the values at I and j to ensure the permutation progresses to the next lexicographical order. Finally, we reverse the subarray starting from I plus 1 to the end of the array, ensuring that this portion is arranged in ascending order, which represents the smallest possible order for these elements. To implement the helper methods, we define swap and reverse. The swap method takes the array in 2 indices, I and j, as input, then swaps the elements at these positions using a temporary variable. This is used earlier to exchange the values at nums I and nums j. The reverse method takes the array in 2 indices, start and end, and reverses the subarray between these indices. It uses a while loop to repeatedly swap the elements at the start and end indices, incrementing start and decrementing end after each swap, until the 2 pointers meet or cross. This ensures the subarray is reversed efficiently. These helper functions encapsulate the low-level operations, keeping the main algorithm clean and more readable. To solve the next permutation problem, let's walk through the first example where the input array is 1, 2, 3. The first step is to identify the rightmost index I such that nums I is less than nums I plus 1. We start by setting I to len nums 2, which is 1. At this index, nums 1 is 2, and nums 2 is 3. Since 2 is less than 3, we stop here and confirm that I is 1. Next, we need to find the smallest number greater than nums I to the right of this index. We set j to len nums 1, which is 2, and check nums 2, which is 3. Since 3 is greater than 2, we stop here and confirm that j is 2. The third step involves swapping nums I and nums j. Swapping nums 1 with nums 2 updates the array to 1, 3, 2. Finally, we reverse the subarray starting from I plus 1 to the end. The portion to reverse is nums 2, which is just 2. Since reversing a single element doesn't change anything, the array remains 1, 3, 2. The final output for this example is 1, 3, 2. Now, let's examine the second example where the input array is 3, 2, 1. As before, we start by finding the rightmost index I where nums I is less than nums I plus 1. Setting I to len nums 2, which is 1, we check nums 1, which is 2, and nums 2, which is 1. Since 2 is not less than 1, we decrement I to 0. Here, nums 0 is 3, and nums 1 is 2. Again, 3 is not less than 2, so we decrement I to minus 1. At this point, we've scanned the entire array and found no valid I. When no such index exists, it means the array is in descending order, and the next permutation is simply the smallest possible order. Therefore, we skip steps 2 and 3 and proceed to reverse the entire array. Reversing 3, 2, 1 results in 1, 2, 3. This is the final output for this example. Finally, let's consider the third example with the input array 1, 3, 2. As before, we start by finding the rightmost index I where nums I is less than nums I plus 1. Setting I to len nums 2, which is 1, we compare nums 1, which is 3, with nums 2, which is 2. Since 3 is not less than 2, we decrement I to 0. Now, at index 0, nums 0 is 1, and nums 1 is 3. Since 1 is less than 3, we stop here and confirm that I is 0. Next, we find the smallest number greater than nums I to the right of I. Setting j to len nums 1, which is 2, we check nums 2, which is 2. Since 2 is greater than 1, we stop and confirm that j is 2. In step 3, we swap nums I and nums j. Swapping nums 0 with nums 2 updates the array to 2, 3, 1. Finally, we reverse the subarray starting from I plus 1, which is nums 1. Reversing 3, 1 results in 1, 3. Updating the array gives us 2, 1, 3. The final output for this example is 2, 1, 3. To analyze the time complexity of the next permutation algorithm, we start by breaking it into its 4 main steps. The first step involves finding the first decreasing element when traversing the array from right to left. In the worst case, this requires iterating through the entire array, resulting in a time complexity of O(n), where n is the length of the array. Next, we identify the smallest element larger than this decreasing element by performing another right-to-left traversal. Again, this operation is linear in the worst case, adding another O(n) to our complexity. The third step, which is swapping 2 elements, is a constant time operation with a complexity of O(1). Reversing the subarray, which is the fourth step, involves swapping elements in pairs from the pivot to the end of the array. In the worst case, this requires O(k) operations, where k is the length of the subarray. Since k can be at most n, this step effectively has a time complexity of O(n). When we combine all 4 steps O(n) for finding the pivot, O(n) for locating the next larger element, O(1) for swapping, and O(n) for reversing, the overall time complexity of the algorithm becomes O(n). It's important to note that this complexity holds for both the best case and the worst case, as the algorithm always performs these steps in sequence. Now, let's consider the space complexity of the algorithm. Because the input array is modified directly, the algorithm operates entirely in place. This means no additional data structures are used for intermediate computations, and operations like swapping and reversing are performed directly on the input. As a result, the auxiliary space required is O(1). Since the algorithm does not require any extra space for outputs or any other processes, its overall space complexity is O(1), making it extremely efficient in terms of memory usage. To put this into perspective, consider a brute force approach that generates all possible permutations of the array, sorts them, and then identifies the next lexicographical permutation. This would require O(n) time to generate permutations and additional time to sort them, resulting in an astronomically high complexity of O(n). Log (n). Clearly impractical for large inputs. In contrast, the optimized algorithm reduces the problem to 3 linear passes over the array, achieving a time complexity of O(n) and a space complexity of O(1). This efficiency is achieved by leveraging a mathematical approach to directly compute the next permutation without generating all possibilities. The sequential nature of the operations and the absence of extra data structures confirm the big O analysis, making this algorithm a significant improvement over the brute force method. When solving the next permutation problem, there are a few common mistakes to watch out for. First, failing to handle edge cases properly can lead to incorrect results. For instance, if the input array has just one element or is already in descending order, these scenarios require special attention. Arrays in descending order, for example, don't have a next permutation, so the output should be the smallest permutation instead. Another frequent issue is incorrect swapping logic. If the elements are swapped incorrectly while reversing the suffix or identifying the next larger element, the result will likely not be lexicographically correct. Lastly, relying on a brute force approach to generate all permutations is a major pitfall. This method, while intuitive, is computationally impractical for larger inputs because its factorial time complexity makes it infeasible as the input size grows. A few additional mistakes to be mindful of include failing to reverse the suffix properly. Once the pivot is found and the swap is made, the elements in the suffix must be reversed to ensure the next permutation is in ascending order. If this step is skipped, the result won't be correct. Another misunderstanding is confusing the next permutation with a fully sorted order. While sorting may seem like the logical step, it doesn't align with the problem's requirement, which is to find the next lexicographical arrangement. This subtle distinction is critical to solving the problem accurately. From an interview perspective, there are key insights to demonstrate your understanding of the problem. One of the most important is identifying the pivot point, which is where the descending order breaks from the right. This is the foundation of the optimal solution and something interviewers often focus on. Efficiently reversing the suffix is another area where candidates sometimes struggle, but recognizing that the suffix is already in descending order makes this task much easier. It's also valuable to discuss the trade-offs between brute force and optimal solutions. A brute force approach, while simple, is not scalable, whereas the optimal approach with a time complexity of O(n) is both efficient and elegant. Additionally, being aware of edge cases like empty arrays, arrays with one element, or identical elements can set you apart. If you find yourself stuck, starting with a brute force method and explaining how you would optimize it step by step shows strong problem-solving skills. This problem also connects to several related problems that can help deepen your understanding. For example, LeetCode 46 and 47 cover permutations and variations with duplicates, while LeetCode 556 extends the concept of the next greater element to integers. Exploring these can provide valuable insights. As for alternative approaches, the brute force method involves generating all possible permutations, sorting them, and selecting the next one. While straightforward, its factorial time complexity makes it impractical for larger inputs. The optimal two-pointer technique, on the other hand, is much more efficient. By finding the pivot, locating the next larger element, swapping, and reversing the suffix, this approach achieves the desired result in linear time. However, it requires a clear understanding of the logic and precise implementation. Another approach worth mentioning is recursive backtracking, where permutations are generated one at a time through recursion. While this method is less efficient due to its factorial time complexity, it can be a useful learning tool for understanding permutation generation in general. By exploring all possible arrangements recursively, you gain a deeper intuition for how permutations are constructed, even though it may not be the best approach for solving the next permutation problem in practice. Great job making it to the end. To recap, we explored the next permutation problem, broke down the efficient two-pointer solution, and discussed its complexity. This technique is not only useful for this problem but also serves as a foundation for solving similar permutation-based challenges. Thanks for watching, and don't forget to like and subscribe for more coding content. See you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!